This video is about problem solving with the chain rule, a very important and powerful computational rule from calculus. In this first problem, the goal is to find a bunch of derivatives with the chain rule, but let's state what the chain rule says first. The chain rule is all about differentiating functions that are compositions of two simpler functions. Like a function g of h of x, we want to take the derivative of such a function when the functions g and h have derivatives themselves. They are differentiable. The chain rule says take the derivative of the outer function. The g is the outer function because it gets done second when you do this composition, g prime. Plug in the inner function, h of x. H is called the inner function because when you compose these two functions, h gets applied first. Then multiply times the derivative of the inner function. So to use this, what we need to do in each case is recognize these functions as compositions of two simpler functions. In part A, f of x is e to the 2x power. Think carefully about what happens when you plug a number in for x. What do? You plug it in right there, which means you multiply by 2 first before you exponentiate. The inside function, the thing that gets done first, is 2x. Then you exponentiate, you raise e to that power. The outside function, the thing that gets done second, is e to the x. So we can write this as g of h of x, where we should say what g and h are. G of x is the outer function, that's e to the x, and h of x is the inner function, that is 2 times x. So according to this chain rule that you see here, when I differentiate f, I need to find the derivative of g first. Well, let's do that here. G prime of x will be e to the x. I need to plug in h of x into that, so I get e to the 2x. When I replace x here with 2x, I get e to the 2x. Then the chain rule says to multiply that times the derivative of h of x. H prime of x here is a constant, the constant 2. So again, I took the derivative of the outside function, g prime, that was e to the x, but then I plugged in the inside function, h of x, that's 2x. I need to replace that x with 2x to get this. Then multiply times the derivative of the inside function. H of x is the inside function, its derivative is 2. I multiply by that. There is the answer for part A. More typically, you would write that as 2e to the 2x. In part B, it's a similar question. F of x equals e to the negative x. Let's go ahead and do the rest of these without writing out explicitly what g and h are each time. We'll just think about it. That is definitely the quicker way to go. F of x is e to the negative x. What is the inside function? What is playing the role of the h of x? What gets done first? That's negative x. Multiply x by negative 1. Then you exponentiate. G of x, the outside function, is still e to the x, but the inside function now for this question is negative x, not 2x. But once again, the chain rule says take the derivative of the outside function. The outside function is e to the x here. But then plug in, replace x with the inside function, which in this case is negative x. Then do h prime, take the derivative of the inside function. The derivative of negative x is negative 1. There's the answer. More typically, you'd write that as negative e to the negative x. And that will be the derivative of e to the negative x. You can always check these things by graphing them as well, and making sure that it does look like the graph of the derivative is telling you slopes of tangent lines to the original function. Part C is a little trickier. What is the derivative of f of x equals e to the x squared? It's a little trickier because it's easy to misinterpret what you're supposed to do here. When you replace x with a number, are you taking e to the x and then squaring the result, or are you squaring first? The answer is, when you use this kind of notation, you are squaring first. The inside function is x squared. We don't do e to the x first and then square. If we had meant to do e to the x first and then square, we would either write that, or by a property of exponents, we'd multiply those exponents and get e to the 2x. So understand that these are different things. There you're multiplying, you're exponentiating first and then squaring. Here you're squaring first and then exponentiating. That's very, very important to realize. And it affects the answer. The inside function here is x squared. The outside function is e to the x. Once again, I take the derivative of the outside function, e to the x, but then I plug in the inside function in place of x to get another x squared there. Then multiply times the derivative of the inside function. The derivative of x squared is 2x. There's the answer. More typically, you'd put the 2x in front and write it like that. That is the derivative of e to the x squared. Part D. Find the derivative of the square root of e to the 3x. I'm going to do this one in two ways. First, let's do it by treating the square root as a 1/2 power. So f of x equals, well, I guess in both cases I'll do that, but I also want to use a property of exponents with this first method here. Treat the square root as a 1/2 power. And then what I'm trying to say with this first method is multiply those exponents to get e to the 3/2 x. That's another way to write the same function. I have not taken a derivative yet. Now take the derivative, use the chain rule. The inside function is 3/2 times x. The outside function is e to the x. I take the derivative of the outside function, e to the x, to get e to the x, but then I replace x with 3/2 x, and then multiply times the derivative of that inside function. The derivative of 3/2 x is 3/2. There's the answer, 3/2 e to the 3/2 x. If I preferred writing it in terms of square roots, I can kind of undo what I did in this first situation. I could put that 1/2 out in front and put as a power like this is what I meant, and then make that a square root, so I could write 3/2 square root of e to the 3x. That would be a less common way to write it. Actually, it would be just simpler to leave it like this. Let me also do this with a chain rule where I use the chain rule twice, really. Let's look at this and realize I could think of this as a composition really of three functions. Take a number x, first multiply it by 3, so the most inside function would be 3x. The middle function would be exponentiation, e to the x, and then the most outside function would be the square root of x, x to the 1/2 power. So if I use the chain rule that way to try to get the same answer ultimately, you have to be careful. The derivative of the most outside function, x to the 1/2, is 1/2 x to the negative 1/2, but then I need to replace x with e to the 3x. Then multiply times the derivative of that inside function, e to the 3x, for which I need the chain rule again. And if you think about it carefully, you'll get e to the 3x times 3. Then simplify. This is 3/2. This is e to the 3x to the first power. I can add those exponents and write e to the 3x to the 1/2 power. And you do see that this is ultimately the same thing that I got before. This is the right answer. Last, we're going to take the derivative of this thing right there, not an exponential function, but a polynomial being raised to a high power, a 100th power. Do I have to literally expand this thing to the 100th power? No, definitely don't do that. It could take you the rest of your life, I think, if you did it. Well, maybe not quite the rest of your life, but a long, long time. Try to find the derivative of this some other way. And the key is the chain rule. Think of this entire polynomial inside the parentheses as the inside function, what gets done first, and raising to the 100 power, x to the 100 power, as the outside function. So let's go ahead and write this function down here so I don't have to keep moving the paper. This is f of x equals x cubed plus 5x squared minus 4x plus 1 to the 100 power. I'll differentiate this with the chain rule. When I finish it, I am also going to give you a little extra treat and show you that Mathematica can actually expand this. Mathematica is a computer program by Wolfram Research, and I'll show you what the answer is, but that's just for fun. What's the outside function again? X to the 100 power. What's the derivative of x to the 100 power? It's 100 times x to the 99 power, but replace x with the entire inside function. This entire thing gets raised to the 99 power. Then multiply times the derivative of that inside function. It's very important to use parentheses here. Students often forget parentheses. I'm going to multiply times the entire derivative of this. It needs to be inside parentheses. 3x squared plus 10x minus 4 will be the derivative of that inside function. Okay, so now let's show you briefly, just for fun, what Mathematica produces when you expand that expression, this entire polynomial to the 100 power in all its glory. There it is. Let's move it up so you can see the entire thing here, if I can click on this. There we go, and look, while those coefficients get humongous, then they get smaller at the end. And your highest power of x is indeed x to the 300 power right there. Isn't that fun? Number 2, as you can see, is kind of an abstract problem where you might have some information you don't actually need to solve the problem, but that's part of the point, is for you to try to decide what information is necessary. You can see ultimately, based on some functional data, we're given a function h that is a composition g of f of x, and we're supposed to compute h prime of 2. The fact that it's a composition means we need the chain rule, okay? So we need to do that and ultimately plug in 2. For any value of x, h prime of x by the chain rule, as we talked about in the first problem, is the derivative of the outside function. In this case, the outside function is g. Plug in the inside function into that derivative and then multiply times the derivative of the inside function. And certainly when I plug in x equals 2, that's got to be true as well. H prime of 2 would be g prime of f of 2 times f prime of 2. Do we have the information we need to finish this problem? We do have f prime of 2, that's negative 1. We also have f of 2, that's going to be necessary to be 8. So this becomes g prime of 8 times f prime of 2, which is negative 1. Do we know g prime of 8? Look over here. Yes, we do. That's 3. So this becomes 3 times negative 1, or negative 3. The other pieces of information, g of 2 being 1, g of 8 being 2, g prime of 2 equaling 3, are not necessary to solve the problem. We need the things that you see here. Use just those pieces of information to solve the problem. In number 3, we're trying to apply derivatives to help us understand a graph of a function. For what values of x is the graph of this function going to be concave down? We'll need to find the second derivative and figure out where it's negative. Turns out we will need the product rule in addition to the chain rule in this problem when we find that second derivative, so we'll get a little bit more practice with the product rule. So the derivative here, first use the chain rule, e to the negative x squared. What's the inside function? What's the outside function? The inside function is negative x squared. By the way, when you see the expression negative x squared, it's understood that you do x squared first and then multiply by negative 1. Because if you had done multiplying by negative 1 first and then squaring, the negative sign would go away. So it is understood that that kind of expression equals this, not that, okay? So this is the inside function, e to the x is the outside function. We need to take the derivative of the outside function. The derivative of e to the x is e to the x. Plug in the inside function, negative x squared, then multiply times the derivative of the inside function, which will be negative 2x. More typically, you'd put the negative 2x out in front. Then take the second derivative. We're trying to figure out where this function is concave down. Here we need the product rule as well. Here's our first function, here's our second function. And when we take the derivative of the second function, we will need the chain rule again. The derivative of the first function, negative 2x, is negative 2. Multiply that times the second function. Then add the first function times the derivative of the second, and be careful about minus signs here, as I'm trying to be in differentiating the second function, e to the negative x squared. It's the same as the original first derivative. I once again use the chain rule, get e to the negative x squared times negative 2x. Be really careful about minus signs. Simplify a little bit. The two minus signs cancel, become a plus sign. 2 times 2 is 4. We get 2x's, gives us x squared. And we get multiplied by e to the negative x squared again. We're trying to figure out where is this negative, okay? It's probably, okay, it could be helpful to figure out where it equals 0. Let's go ahead and just put the inequality like that right away. We're supposed to solve this inequality for the values of x that will make that true. Doesn't look very easy, does it? Well, it's easier than it looks. The key thing is to factor as much as possible out of the first these two terms here. Is there a common factor? Certainly there's a common factor of 2 that can be factored out. There's also a common factor of e to the negative x squared. That can be factored out. What's left? If you factor it out like this, what's left here is a negative 1. And what's left here is a plus 2x squared. We're trying to figure out what values of x will make this negative. This thing is always positive, no matter what x is. So the sign of this product is completely determined by the sign of what's in parentheses here. This is equivalent to negative 1 plus 2x squared being negative. That's equivalent adding 1 to both sides, to 2x squared being less than 1. That's equivalent to dividing both sides by 1/2 to x squared being less than 1/2. And careful, that's equivalent to the absolute value of x being less than the square root of 1/2, which is the same as 1 over square root of 2, which is the same as square root of 2 over 2. You need the absolute value signs there if you're going to be accurate here when you take the square root of both sides. X could be positive or negative here. This, if you want a little bit more detail about what this means x itself is between negative square root of 2 over 2 and positive square root of 2 over 2, an interval centered at 0. That's where the graph is concave down. If you're going to write the answer in interval notation, you could say it's concave down on the open interval from negative square root of 2 over 2 to positive square root of 2 over 2. You might even argue it's concave down still at the endpoints. Those are technically what's called inflection points. More on that in a second when I draw the graph. Probably you could say the answer is either way. Those points are where the second derivative actually equals 0. In set builder notation, you could say this is the set of all real numbers x, the set of all elements of the real numbers, such that x is between these two numbers, negative square root of 2 over 2 and positive square root of 2 over 2. Let's go ahead and graph this function. Square root of 2 over 2, I believe, is about 0.707, something like that. This interval is centered on 0, negative square root of 2 over 2, and positive square root of 2 over 2. And it turns out, you can check this on your calculator, that the graph of this function looks like, well, it's called a bell-shaped curve. It's going to look about like this. And you can see it is concave down between these 2 points. That's where it looks like a frown. Concave down looks like a frown. What does concave down really mean? It means slopes are decreasing. The derivative f prime is decreasing between these two values of x. And it's concave up. Otherwise, at these 2 points, you have changes in concavity. Those are called inflection points of the graph. And you can also think about where this function is increasing or decreasing based on the sign of the first derivative. It's a bell-shaped curve. It's related to something very important in statistics called the normal distribution. Problem 4 is a population growth word problem. The population P of Minnesota, a state in the United States, in millions of people at time t years after the year 2000 is approximated by this function that you see right here, an exponential growth function. Part A says, based on this formula, find an estimated population in the year 2019. That's a few years ago. I'm making this in 2022. Include units. And then in Part B, based on this formula, how fast is the population changing in the year 2019? Include units there. So a basic function and derivative problem. But we do need the chain rule. That's why it's in this video. The inside function is 0.00754 times t. And the outside function, you could say, if you like, is 4.919 times e to the t. Let's give this function a name. Let's call it f of t. If you're not given a name, you can certainly give the function a name like I just did. In part A, we're trying to find the population in the year 2019. That's 19 years after the year 2000. We're trying to find f of 19. Some people might write p of 19, but technically that's abusing notation because p is technically a dependent variable, not a function name. What does this give us? It gives us 4.919 times e to the 0.00754 times 19. Go ahead and compute this. It's going to be something probably bigger than 5 million. What's the actual answer? I don't know offhand. I didn't look it up. 4.919 times e to the 0.00754 times 19 power. Make sure I type everything correctly. I think that looks good. About 5.677, if you round it, million people would be the units, okay? You could go ahead and look it up and see how accurate this is, okay? This is a model. It's not going to be completely accurate. And to tell you the truth, if I had to guess, is this too big or too small? I would guess maybe too big, though that could be wrong. The population growth rates in terms of births per 1,000 people or something has gone down over time, especially since the year 2008 and especially since COVID. So, I mean, COVID in 2019 hadn't occurred yet, but I'm thinking maybe this is too big. But there's also immigration to take into account, migration from state to state, that kind of thing. So who knows for sure? You can look it up. All right, part B. Based on the formula, how fast, derivative, rate of change, is the population changing in the year 2019? In function notation, we're trying to find f prime of 19. In Leibniz notation, which you should also know, we're trying to find dp dt, and we're trying to evaluate that at time 19. But we need the chain rule, is the point here. Let's go ahead and write the derivative of this with the chain rule and with the variable t, and we'll once again use an evaluate symbol at the end, so I'm going to plug in 19 at the very end. It's not maybe the best notation here, but we're stuck with it at the moment. The derivative of the outside function, 4.919 times e to the t, is itself 4.919 times e to the t. But remember, with the chain rule, you need to plug in the inside function. So I get a 0.00754 times t. And then the chain rule says multiply times the derivative of that inside function. That's going to multiply by 0.00754. And actually now if you plug in t equals 19, and if you think about what just happened, that's the same as the original function value at t equals 19. So I can take the previous answer and I can just multiply by 0.00754. That's very interesting and nice that you can do that. Nice property of exponential functions with base e here. And so I just take this previous answer, I've already computed that part, just multiply this now by 0.00754 to get about 0.0428. What are the units? This is very important. This would be million people per year. That's the rate of growth, the instantaneous rate of growth, or the estimate for the instantaneous rate of growth in the year 2019. The population is growing by that many people per year, approximately. Probably makes more intuitive sense if we convert this to like thousands of people per year. To convert millions to thousands, you multiply this decimal by 1,000, which moves the decimal point to the right by 3 spots. This would be the same as 42.8 thousand people per year. That's a little easier to get your mind around. You know, that's like the population of a medium-sized city or town, depending on the terminology you want to use in a given year. Number 5 is an abstract compound interest problem. If you invest P dollars in the bank account that has an annual interest rate of R%, realize here R, for example, if it's a 4% interest rate, would be the number 4, not 0.04 in the way this is set up. So you got to be careful. The percent sign is a signifier for that. It's compounded twice per year. Then after T years, you will have A dollars according to this formula. So I use the compound interest formula, and I essentially divided R by 100 and also by 2 because of compounding twice per year. And I raise this to the 2t power. The 2 in this case is sometimes called n in the compound interest formula, the number of compounding periods per year. If R were a decimal without a percent sign, like a 0.04, I would not divide by 100. I'd have R over 2 instead of R over 200. It's going to be easier to interpret derivatives though, thinking about it this way. Part A says, find dA dt, assuming P and R are constant. Treat P and R as constant and T is the independent variable. Then interpret that. What does it represent? Then in part B, we're going to find a different derivative. dA dr. Assuming P and T are constant, we're making different assumptions about what's constant. Is that okay to do? Yes. Whether a letter represents a constant or a variable is all in your head. It's all in how you're thinking about it. I emphasize this all the time to my students, and it's very important to realize you can do that. We also want to understand what that represents. We'll want to think about units for these derivatives and interpret them as rates of change. I'm not going to bother plugging in numbers for these things, but you certainly could to make it more concrete, okay? But I won't take the time to do that. Before I take the derivative, or as I take the derivatives here, I also want to mention that you will sometimes see these derivatives written in an alternative notation with, instead of an ordinary looking d, kind of a curvy looking d like this. That's called partial derivative notation. That's related to multivariable calculus. And it's kind of highlighting the fact that I could actually think of, well, P, R, and T all as being quote-unquote variables if I wanted to. And when I use this notation, I'm kind of emphasizing that I'm treating the other variables as constant. It's kind of a weird thing to do. Does it really matter? Does it really matter whether you use an ordinary D or kind of a curvy D? It doesn't really matter, okay? It's just notation. It's just meant to communicate something. Don't get scared off by it is all I'm trying to say. If I treat P and R as constant and T as the variable, this becomes an exponential function of T. I need to know about derivatives of exponential functions. I also need the chain rule because the inside function there is 2t instead of just a plain t. The base is not e. This is not a continuous interest rate here. It's an annual effective interest rate, you might call it. Actually, it's nominal since it's compounded twice per year. So this is a little tricky. This is like my base. I'm going to need to have a factor of the natural log of this base in this derivative. So it's kind of going to be a complicated looking derivative. The p is a constant. It just gets carried along for the ride. Let me go ahead and multiply times the natural log of this base, 1 plus r over 200. Then times that base, 1 plus r over 200. To the 2t power, I'm taking the derivative of the outside function here, and now when I write 2t instead of just a t, I'm plugging in the inside function. And then the chain rule says multiply times the derivative of the inside function, 2. This crazy looking expression, a product of 1, 2, 3, 4 things, is the derivative of this thing, okay, when you think of this as a function of t and treat p and r as constants. I'm not going to write out what it represents, but let me just describe it. We should write out its units at least. It would be units of A per unit of T. A is in dollars, A is an amount in dollars, and T is time in years. This would be in dollars per year. So if you took particular numbers, like maybe P is 1,000, R is 4, and a particular moment in time like T equals 5 or something, and plug those numbers in here, you would get a number. And that number, whatever it is, would represent how fast the amount A is growing at time t in dollars per year. It would be a rate of change with respect to time. So then if you let time go a little further, you'd multiply that rate of change times the change in time to estimate the new amount a short time later. This is fundamental stuff to know. I'm just describing it verbally. Try examples. I would encourage you to do that. Part B, again, we're finding the derivative dA dr, the rate of change of A with respect to R in partial derivative notation. I'd use a curvy kind of D, like that. But again, that's just notation. Don't worry about it. Don't let it scare you off. Differentiating with respect to R, treat the P and T as constant, okay? And I'd be thinking about small changes in the interest rate instead of small changes in time if I want to interpret the derivative. As a function of r, treating the p and t as constant, this is not exponential. It's, well, I guess you'd call it a polynomial if 2t is a whole number at least. That could be expanded out if you wanted to, though like at the end of problem 1 in this video, we would not want to expand it out. We'd want to use the chain rule. Differentiate it as is. What's the inside function? The inside function would be 1 plus r over 200. What's the outside function? P times, what should I call it, x to the 2t power, where x is the variable. 2t is a constant here. 2t is like an n or something. So, careful. The derivative of that outside function, it's really a constant times a power function. You got to use the power rule. You got to bring down the 2t in front. What you may have wanted to do in part A, but you shouldn't have done in part A. Bring down that 2t. Got to subtract 1 from that exponent as well. I'm plugging in the inside function and subtracting 1 from the exponent, 2t minus 1. Then multiply times the derivative of this inside function with respect to r. Derivative of 1 is 0. Derivative of r over 200 is 1 over 200. Plug in numbers to interpret this as a rate of change. Units of A per unit of R. Dollars per percent. It's actually better to say percentage point. Percentage point instead of percent because, well, if you say percent, it can easily get misinterpreted. If you let r, say r starts out at 4% and increases to 5%. As a percent growth, growth from 4 to 5 is 25% growth. But that's not what you want to think about if you're thinking about this rate of change. You want to think about the fact that delta r, the change in r, is 1. And what we say is it's 1 percentage point. Even though it grew by 25% from 4 to 5, anything that grows from 4 to 5 grows by 25%. We want to emphasize the change in r not as a percent, but as an actual amount, you might say. And we use the phrase percentage point. That is what people use. So again, plug in particular numbers to help you understand this as a rate of change, to help you estimate changes in A if you let r increase a little bit. Our final problem is kind of a fun problem to derive the quotient rule using the product rule and the chain rule. Let f and g be differentiable for all x, having derivatives for all x, and let q of x be the quotient, f of x divided by g of x. By writing q of x equals f of x times g of x to the negative 1 power, which we certainly can do, use the product rule, chain rule, and some algebra to derive the final form of the quotient rule as it's usually written from the last video, and this is the way I say it. Low d high minus high d low over the square of what's below. The low function is g of x, the high function is f of x. Low d high means the lower function times the derivative of the higher function. Minus high d low means the top function, the high function, times the derivative of the low function over the square of what's below, meaning square the lower function. That's the final form of the chain rule. So what do we want to do here? We want to differentiate q of x written like this, where we don't need the quotient rule, but we can use the product rule and chain rule now. What is q prime of x here? It's a product, first of all. So it's the derivative of the first function, f prime of x, times the second function, g of x to the negative 1 power. We don't need the chain rule there. Plus the first function times the derivative of the second, g of x to the negative 1 power. I definitely need the chain rule there. Think about it with me here. The inside function, focused on this part there, is g of x. That's what gets done first. The outside function is raising to the negative 1 power. You could say x to the negative 1 power. The chain rule says take the derivative of that outside function. The derivative of x to the negative 1 power by the power rule would be negative 1 x to the negative 2 power. But then replace x with the inside function, g of x in this case. That gets raised to the negative 2 power. Then multiply times the derivative of that inside function. There is q prime in a not standard form. We need to write this in the standard form to help us finish this problem. We want to write things as fractions. This is f prime of x divided by g of x. And then we have minus, write this entire thing as a fraction. You'd have f of x times g prime of x divided by g of x quantity squared. And again, I put the negative sign in front to compensate for that negative 1. This is a difference of two fractions. We need a common denominator. This one has a denominator of g of x. This one has a denominator, the bottom, of g of x squared. To get a common denominator, I need to multiply this one by g of x on both the top and the bottom. It doesn't change the function because I'm really multiplying by 1. That's going to give me that common denominator. And now that I've got that common denominator, I can now subtract these two fractions by subtracting their numerators. And I get, I'll write it in the form I usually write it, low d high minus high d low over the square of what's below. Assuming everything is differentiable, technically assuming we're not dividing by 0, we have derived, not proved because we haven't written sentences, but we have derived the quotient rule with the product rule and chain rule. Thanks for watching.